Hello everyone and welcome to lecture 33. So we are talking about the producer theory. We started with the one input production function, Q as a function of L, where L is measured in labor hours, right? And that helped us to define and state the law of diminishing marginal returns, right? Which said that if you have a fixed input, the marginal product of the firm's variable input, in this case labor, first increases and then eventually diminishes. The one input production function does not capture substitutability between two inputs, right? So we moved to a model of more than one input, and the simplest such case is the one which has two inputs. And we said, let's look at a production function which has labor and capital as the two inputs. So we defined Q as a function of labor and capital, and again we defined marginal product of labor and marginal product of capital. So the marginal product of labor is the change in output resulting from a unit change in labor keeping capital constant. Similarly, the marginal product of capital is the change in output resulting from a unit change in capital keeping labor constant. And why did we care about the marginal product of labor and marginal product of capital? Because we used these terms to derive the slope of the isoquant. Recall, isoquant, iso means same and quant is a short form for quantity. So isoquant is essentially the set of all labor capital, i.e. the input combinations which are on the same level of output, right, which give the firm the same level of output. And isoquants look similar to indifference curves, it's just that they are representing output levels, and output levels have a physical interpretation, right. So we also stated a very important part of this discussion, which is defining the marginal rate of technical substitution, which was essentially the slope of the isoquant, right. And we used the definition of MRTS, which is minus MPL by MPK, to look at a few examples. So we looked at a production function of the form Q is equal to f of L is equals to L times K, right. So we looked at a production function of the form L times K, right. Then we also looked at a production function of the form 2L plus 3K, right, which is linear in labor and capital. And we figured out that the marginal rate of technical substitution for a function of the form 2L plus 3K is constant, and we learnt it is minus 2 by 3, the units of K over units of L. Okay. So what we will do today is we will introduce two very interesting ideas. One is returns to scale, and the second is we will define formally what we mean by opportunity cost. Okay. So we will get to them one by one. Now, why returns to scale? Now recall, marginal product of labor allows you to measure the change in output resulting from a unit change in labor, but in that process you are keeping capital constant. Similarly, marginal product of capital is allowing you to measure the change in output resulting from a unit change in L, keeping labor constant, unit change in K, keeping L constant, right. So when you are measuring, so the marginal product allows the change in output when only one input is changed. And in that process, all other inputs are kept constant. So to get MPL, you are changing L and keeping K constant, and you are getting MPL. Similarly, you are keeping L constant, changing K, and getting marginal product of capital. But a firm may be interested in changing both the amount of labor and the amount of capital. To be more specific, a firm might want to either double or triple the amount of labor or the amount of capital. So what happens to output when the firm is changing both labor and capital simultaneously by some proportion? So returns to scale is the concept which is going to allow us to understand what is going to happen to output. Okay. So let's look at a production function f of Lk. We'll keep it general and then I'll take specific examples. So Q is equal to f of Lk as before. Now we take some factor lambda which is greater than 1. Okay. So why greater than 1? Because it's easier to visualize this as a lambda equal to 2 will mean doubling the inputs, right. So I had some amount of labor, some amount of capital. I have taken lambda to be equal to 2. So I'm doubling the amount of labor and amount of capital. If lambda was 3, the inputs are actually tripling, right. So Similarly, once I have lambda greater than 1, what I mean is that suppose L and K are scaled up to lambda L and lambda K, right. So, initially I had the input bundle as L comma K. That input bundle based on the technology gave me an output which is given by Q is equals to f of Lk. Now, I am scaling up labor and capital to lambda L and lambda K, and I want to understand what has happened to Q dash equal to f of lambda L lambda K, right. How does this compare to f of lambda L lambda K? Okay. So, let me define 3 terms. So, this is the new output, and we want to understand how does the new output compare to the previous output f of L comma K. Now, let me first define the 3 terms. So, the first term is if f of lambda L lambda K, right, f of lambda L lambda K. So, you scaled up the inputs by the factor lambda, your new output is f of lambda L lambda K. If this is greater than lambda times f of L comma K, right, you doubled your inputs, your new output more than doubles, right, it increases by a factor greater than 2. You say that your production technology exhibits increasing returns to scale. And we will denote it by IRTS, right. So, if you are taking lambda to be equal to 2, so essentially what you did was you are doubling the inputs, scaling up the inputs by a factor 2, you find out what the new output is, that output perhaps has increased by a factor, let us say 3 or 3.5. So, the key aspect is that it has increased by a factor greater than the factor in which you increase the inputs. So, output, so for example, you double the inputs, the new output more than doubles, right. Let us take a specific example. So, suppose I have the example where I have a cylindrical pipe and let us say you are transporting water, right, through this cylindrical pipe, and output is being measured by the volume of water that is being sent, right. So, I have a cylindrical pipe, right, the radius is r and the length is L, and I am measuring output in terms of the volume is the amount of water. Now, the volume is simply going to be pi times r square times L, right. So, the factor pi multiplied by the square of the radius times the length of the pipe. So, initially instead of labor and capital, my inputs were the radius and the length, and the volume of water that I was able to send from point A to point B was pi times r square times L. Now, suppose I double both the radius and the length, right. So, the r is increased to 2 times r, right. So, I have doubled the radius of the pipe and the length of the pipe is increased to 2 times L. Okay. I want to find out what has happened to the new volume. Well, recall the volume is pi times the radius, which is 2 times r now whole square, times L, which is 2 times L now, right. So, the new length is twice of the previous length. So, the new volume is pi times the radius square times the new length, which is nothing but, so this is going to give me a 4 times 2. So, that is going to be 8 times pi times r square times L, and pi r square L is nothing but my previous volume. So, this is 8 times the previous volume, which is clearly greater than 2 times V. So, I doubled both my inputs, both the radius as well as the length of the cylindrical pipe were doubled, and I end up with a new output which is measured in volume of water, which is increasing by a factor greater than the factor by which I changed the inputs, right. So, this is an example of a production technology which is exhibiting increasing returns to scale. Okay. Similarly, Let's look at an example where if f of lambda L, lambda k is less than lambda times f of Lk. So, you have doubled the inputs, but your output, the new output has less than doubled, right. So, this is called decreasing returns to scale. DRTS. Okay. Now, I will simply say that you have doubled the inputs, the new output less than doubles, right. So, that is the key part here, less than doubles. Now, what is one way to think about decreasing returns to scale? Now, so imagine that you are currently operating from your town, right. So, you are running your operations from your place of stay, and for whatever reason you have decided to expand, right. You are hiring more labor, you are setting up one more office at some other place. Initially, that is giving you better returns in the sense that your revenues are increasing, your cost is also increasing, but let us say your revenues are increasing more than by the factor by which your cost is increasing. So, overall your profits are increasing, right, and you are able to deliver more number of goods and services to your customers. But eventually, as you keep expanding to more and more cities, what happens is the fact that managerial talent is in short supply tells you that as the firm is becoming bigger and bigger, you alone cannot micromanage every single aspect of this firm. So, you will have to delegate responsibilities to heads of different units, and these heads of different units may not have the same managerial ability or the talent. So, decreasing returns to scale is a manifestation of the fact that managerial talent is available in short supply, right. That is one reason why you see decreasing returns to scale. So, you are increasing your labor and capital by a factor 3, let us say, but your output is not increasing by that factor, it is increasing only by a factor, let us say 2. The third example is that if f of lambda L, lambda k is exactly equal to lambda times f of L comma k, which is to say that you increased labor and capital by a factor 2, you doubled your inputs, your new output exactly doubles. This is called constant returns to scale. Denoted by CRTS. And for completeness, we will just mention that you double the inputs, new output exactly doubles. What could be one example? So, suppose you have a call center, right. So, the call center has, so you have one office and there are certain number of people who are working in that call center. So, the output is based on the number of calls that are being handled. Now, you open one more office, right. So, you have doubled, so your inputs are the labor and the office. So, you set up one more office and you have exactly increased L also by the same factor, right. So, if there were 10 people in your previous office, now the number of people in the new office is also 10. So, you have doubled all your inputs, the number of office went from 1 to 2, the L increased from 10 to 20. So, the number of calls that you are handling exactly doubles, right. So, that is an example of constant returns to scale. So, why are we concerned with returns to scale? Because returns to scale will tell us something very useful about market structures when we talk about it later in the course, right. So, keep these three things in mind about what increasing, decreasing and constant returns to scale are. And one more subtle point here is the returns to scale concept is telling you something about your production technology, right. Increasing returns to scale is telling you something about your production technology. You double the inputs, your output more than doubles. So, let us take some examples. So, suppose I have a production function. So, suppose I have a production function which is given as Q is equal to f of Lk equals some parameter A times L to the power alpha k to the power beta, right, where alpha and beta are some parameters. So, what is it that we are interested in identifying? We are interested in finding for what values of alpha and beta, right, under what conditions on alpha and beta does the production technology exhibit increasing returns to scale, decreasing returns to scale, or constant returns to scale. So, let us think about this. And the way to identify increasing returns, decreasing returns and constant returns is to always start with scaling up the inputs by the factor lambda. So, f of lambda L lambda k is equals to a times lambda L to the power alpha lambda k to the power beta, which is equal to, now notice I can essentially write this as lambda to the power alpha. So, a times lambda to the power alpha L to the power alpha times lambda to the power beta k to the power beta. I will combine this lambda to the power alpha and lambda to the power beta, right. So, since the lambda is common here, I can essentially add the powers here. So, I will write this as lambda to the power alpha plus beta times a L to the power alpha k to the power beta, which is nothing but my production function lambda alpha plus beta f of L k. So, what do I know? I now know that f of lambda L lambda k is equal to lambda alpha to the power alpha plus beta times f of L k, right. So, this is what I have figured out. By scaling the inputs by some factor lambda, we have found out what the new output is. Now, let us look at increasing returns to scale. For increasing returns to scale, what do I know? I need f of lambda L lambda k to be greater than lambda times f of L k, right. Recall the definition. I scale the inputs by some factor lambda, my new output has to increase by a factor which is greater than lambda times f of L k. But I already know that f of lambda L lambda k is essentially this entire expression. So, I can basically say, I can replace, instead of f of lambda L lambda k, lambda to the power alpha plus beta f of L k should be greater than lambda times f of L k, right, for to get increasing returns to scale. So, I can cancel the f of lambda L lambda k together. So, what do I have? I have lambda to the power alpha plus beta greater than lambda. If you prefer, you can divide it by lambda here and rewrite this as lambda to the power alpha plus beta minus 1 is greater than 1, right. So, I can even make a statement directly from here. Alternatively, I can say this the same way, that this is lambda to the power 0, which essentially implies that alpha plus beta minus 1 is greater than 0. So, alpha plus beta must be greater than 1. I could have also made that statement directly from this statement, but if you really want to split this into further steps, this is the condition I need for increasing returns to scale. So, the sum of the powers alpha and beta must add up to a number which is greater than 1. Similarly, what about decreasing returns to scale? Well, I need f of lambda L lambda k to be less than lambda times f of L k, right. If I scale up the inputs by some factor lambda, my new output is f of lambda L lambda k, that is less than increasing by the same factor, right. So, that is less than lambda times f of L k. Again, I will replace f of lambda L lambda k by the expression here. So, lambda to the power alpha plus beta f of L k is less than lambda times f of L k, right. So, now I can cancel these two terms from both sides, which will give me lambda to the power alpha plus beta minus 1 is less than 1, and this is nothing but I can write this as lambda to the power 0, which gives me that alpha plus beta minus 1 has to be less than 0. So, alpha plus beta has to be less than 1. So, this is the condition I need for decreasing returns to scale. And finally, you would have correctly guessed the condition that you will need for constant returns to scale. For constant returns to scale, when I change the inputs by the factor lambda, the new output exactly changes by the same factor. So, I have f of lambda L lambda k equals lambda times f of L k. I replace this expression by lambda to the power alpha plus beta f of L k, because that is the expression I have, is exactly equal to f lambda times f of L k. And I can now cancel these two expressions from both sides, giving me lambda to the power alpha plus beta minus 1 equals 1, which is lambda to the power 0, which essentially means alpha plus beta minus 1 is equal to 0. So, alpha plus beta equals 1, right. So, to summarize, we have now identified the conditions on alpha plus beta. So, if alpha plus beta is greater than 1, our production technology exhibits increasing returns to scale. If alpha plus beta is less than 1, the production technology exhibits decreasing returns to scale, and if alpha plus beta is exactly equal to 1, I have constant returns to scale. So, similarly, if you have different production technologies, you can identify or you can say some things about returns to scale. As an exercise, try the following example. What if your production function f of L k was square root of L k, right? So, you scale it up by a factor lambda and find whether this is exhibiting increasing returns to scale, decreasing returns to scale, or constant returns to scale, right. So, you should try this example where f of L k is square root of L k and convince for yourself what is happening when to the new output. Does it increase by more than a factor lambda, less than a factor lambda, or exactly equal to the factor lambda, right. And as I said, so returns to scale will become very useful once we get into market structures a little later in the course. Okay. So, the other related concept that I want to talk about now, and which is sort of the main purpose for doing this example, is this notion of cost and cost minimization. Okay. So, this is the fundamental point of producer behavior, right. Now, what is it? Recall the objective that we had listed last class. The objective is that an efficient producer or a firm would seek to produce some level of output at the lowest possible cost. This is the essence of cost minimization, isn't it? That you want to produce a certain level of output, but you want to produce it at the lowest possible cost. So, before we get to cost minimization, let us spend some time understanding the notion of cost. We have used the word cost multiple times in the course. In fact, we have defined marginal cost. When we looked at marginal analysis, we had looked at a firm which was producing CDs, and we defined, we introduced a cost function for the firm, right. So, the notion of cost in economics, cost always means opportunity cost, right. So, whenever we are using the word cost, even earlier when we looked at the firm which was producing CDs and we wrote down a cost function, C as a function of Q is equal to something, we had in mind, we had actually written the opportunity cost of the firm, right. So, all through this course, whenever we use the word cost in economics, we have in mind the notion of opportunity cost. Okay. So, why are we specific about opportunity cost? Well, the most common concept of cost, the common notion of cost is what is called as accounting cost, which is also the explicit cost, right. So, the most common notion of cost is your accounting cost, which is explicit cost, and you can think of explicit cost as the cost incurred by the firm where you can assign a monetary value to the various aspects of production, right. So, So think of, so I would call this as the direct monetary expenses incurred by the firm in the act of production, right. So for example, you are operating a factory, you are employing some number of workers, you have to pay them a wage, so that is an expense that you are incurring. You are having some machines, so you have got to pay rent for the machines. You are operating it on a piece of land for which you have to pay a rent. You are consuming electricity, so the number of units times the per unit rate is your cost of electricity. You are using several other raw materials, so all of that incurs some cost. So all of that, notice, for all of those inputs you are able to assign a specific or a direct monetary value, right. So I will just say, so this is the cost of raw materials, the cost of labor, rent that you pay for machines, electricity use, etc. Right. So these are the explicit or the accounting costs. Loosely put, if you have a balance sheet and you look at your expenditure column, the numbers, all of those expenditure columns are going to have some monetary value. So you could think of accounting costs as all those explicit costs for which you have assigned a direct monetary value. In addition to this accounting cost, there is also something which is called as implicit cost, right. As the name suggests, these are costs for which a direct monetary value is harder to assign, right. So in economics, you also focus on implicit costs, and let me first write it, that these are costs for which assigning a direct monetary value is difficult. Rather, you can think of it as the income foregone. So they do not involve an explicit monetary value or a monetary component. So you could think of it is the income foregone when a producer uses a resource for a specific activity instead of its alternative use. Right. So your resource could have multiple uses. So imagine that you are operating you are running your business from your home, right. So there are some explicit costs involved, right. The cost you are employing people, you have some computers, printers, some machines in your home or your office. Then you are paying for electricity, you are paying for stationery. So there are all these expenses for which you have assigned a direct monetary value. So these are all explicit costs. However, in addition to this explicit cost, there is also an implicit cost, because since you are operating from your home, you could have given your one room in your home and let it out or given it out on rent to somebody else who would have paid you a rent for using that room, right. Now because you are using your home and that room as part of your office activity, you are not able to rent out that space, and because you are not able to rent out that space, you are foregoing the income, in this case the rent, that you could have potentially earned. So for example, if you are using your home to run your business operations, the implicit cost is the rent that is foregone, right. Now, if you don't capture this rent that is foregone, you would be underestimating your entire cost of operations. You already have your explicit cost, but if you don't factor into account the rent that you could have potentially obtained, you would have underestimated your cost of operations. So, opportunity cost is the sum of the explicit cost and implicit cost. So, whenever we use the word cost, keep in mind that in addition to the explicit cost, we also have the implicit cost, and for us, the sum of both the explicit and the implicit cost is the opportunity cost. We will take a few examples and understand this concept better. We will do that in our next lecture. Thank you.